So the strength of string theory then is it's an extension of traditional physics. It replaces the enigmatic 0D particle with an intuitive 1D particle, and it promises unification of physical theories at Planck length. Again, we've already talked about this, but that's the extension of traditional physics. We started with Newton's gravitational theory. Einstein modifies that to get relativity. Then Planck discovers quantum, and Dirac uses the constant C to get the relativistic quantum theory. And these efforts then lead to the two most successful theories of modern physics. And the next logical step is, hey, we need to combine them all, and that's what string theory does. Well, let's go after it. That should be where we go. When we say intuitive 1D strings, we mean it leads to a consistent finite concept of gravitons, like we mentioned, this idea of quantum gravity. It hints at a structure with all the elements of the standard model, with the bosons and the fermions and even the gravitons, and it replaces general relativity then at these small scales where general relativity would break down. It has this particle called the graviton that enables us to get by that. And it eliminates black hole violation of the quantum theory we just seen, and it promises eventual explanation of the Big Bang singularity. So, hey, that looks good. And now, of course, all of this, again, depends on this supersymmetry, don't forget. We got to have supersymmetry where we got this double number of particles in the universe, or it doesn't work. The whole thing is called off. So they're really hoping to find supersymmetry because it helps unify the forces. It explains the mass hierarchy, which we haven't gotten into much, but it predicts a candidate for dark matter. I'm sure you've heard of dark matter, which is supposed to be 90% of the matter in the universe. Right? So supersymmetry, we've got everything hanging on that. In the meantime, they're building the machine as fast as they can. Won't be ready to turn on until the end of this year or early next year. And in the meantime, string theory gets really popular. See, it started off for physicists when it was embraced when Schwartz FedExed that paper, that draft of his paper, to Ed Witten. And Ed Witten, everybody's eyes on him, so they got all excited, and that's when everybody started getting on board with string theory. And then Stephen Hawking published a book, what was it called? The End, not the End of Physics, but something to that effect that is kind of like Lord Kelvin's statement, before the end of the 19th century, that, hey, we're going to have all this put together and tied up by the end of the century. Of course, he had to retract that. But in the meantime, Brian Greene, now I know you've seen this. Brian Greene,
a very good book.
Yeah, it is. Are you? Okay, so that really, and there's a NOVA program. Have you seen the program on TV? Yeah, it's called The Elegant Universe, and they dramatize it. They got great computer graphics. It's online.
It's available on the internet.
Yeah, it's online. If you want to watch it now, you don't have to buy it. I mean, you can watch it on the internet. Just Google it. But it fired up the public imagination about these string theories and this multiverses that it's developed into now, and brains and all this stuff with quantum mechanic weirdness and all that stuff. So it's really gotten popular, but at the same time, with the physicists, there's really a lot of problems. But this is what the David Pulitzer, who was one of David Gross's colleagues and one winner with him of the Nobel Prize in 2004, said many leading physicists were inclined to conclude in the late 1970s that the task of basic physics was nearly complete and we'd soon be out of jobs. Hawking titled his lecture, that's the one I'm trying to think of, Is the End in Sight for Theoretical Physics? And he argued strongly for the affirmative. He thought the end was there, but of course he had to retract it because once again, big surprise. They hadn't found supersymmetry, which, for 40 years they've been working this thing, 4 decades almost. That's a long time, see? and yet no supersymmetry. They're building this huge machine at fantastic cost to try to find it. So maybe they'll find it, but in the meantime, there's been some other developments that have really been devastating for string theory, and this one is really big. It's not unique, and therefore it can't predict anything. And we'll explain how it's not unique. When we say unique, there's not just one thing, string theory. There's solutions, quote unquote, for you can make it do whatever you want it to do. And then this one is really big, probably the showstopper, because the galactic expansion is discovered by measurement is expanding with time. It's increasing. The rate of expansion is increasing. Well, okay, so our string theory problems then start to mount up because, first of all, it's always been such that it required more physical dimensions than are observed. Can you think of what 26 dimensions or even 10, 6 extra space dimensions mean? Well, there's ways they can compact them and so on and make it work mathematically. And with supersymmetry, they were able to reduce the 26 down to 10, which means 6 extra dimensions of space. But again, supersymmetry hasn't been observed. Now, this unique theory makes the theory, the fact that it's not unique anymore because there's so many ways to wind up these extra dimensions makes it non-predictable. And so, and that's what this, I'm getting ahead of myself on the bullet anyway. It leads to what they call the landscape when you apply string theory to the Big Bang scenario in the history of the universe and what they call inflation, the hot Big Bang. What happens is that leads to like 10 to the 500 possibilities where physical constants can take on different values. And each one is different, meaning a different universe. And the only reason some think that we are able to observe this universe is it just happened to have, there's no way to predict it would have it, but it just by chance happened to have the right constants to make it habitable by life. That's called the anthropic principle. And then again, strings are down there where it's just totally impossible to observe them. So now this idea, see, mathematically, if you take dimensions 2 to the 0 here, and then go up 2 to 1, 2 to 3, 2 to 0, 2, 1, 2, 2 to the third. This is as far as geometry goes. Those are called the Grassmann numbers in there. But the string theory went beyond that, see, to 26 dimensions. And so when they added supersymmetry, it took them back down into this realm here of Euclidean geometry, sort of. And we still had 6 extra, but that's a heck of a lot better than 26 extra. So that was good. And then, but when they got they got into that 10 dimensions, they found that there were different string theories. They were incompatibles. And they call it superstring theory when you add supersymmetry to it. So there are 5 incompatible superstring theories in 10 dimensions. But they then turn out, and this is when Ed Whitten just really wowed everybody, because he was going to give a talk like this, like I'm giving, kind of, to everybody who's coming to hear him give a talk on string theory, but they were string theorists, and they had all these problems because they had gotten down to here, but they had these 5 incompatible string theories in supergravity, something called supergravity. And he decided he better have something interesting to tell them. So on the way, he came up with what they now call M theory, that showed that all of these 5 were just aspects of one theory. They didn't know what the theory was, but they had to be, it was because of this duality, they were dual to one another. So they were like that elephant. They blind men on that elephant. They were just looking at different parts of it. See? And he showed them that, and he didn't tell them what M stood for. Something it's an upside down W for Whitten. But it might be mother theory of all, or magic, or matrix, or whatever. All right, so at the LHC at CERN, they're searching for it, hope to find it. And now but in the meantime, they're building that at CERN, but in the meantime they found out, they were really excited about how to compact those extra dimensions. this is actually a 6-dimensional thing called the Calibi-Yau manifold. And they were all excited because this is really considered to be beautiful, and it determines, you can't read that, but it says, this is, again, this chart is David Gross. But he's saying the nature of the forces, the form of matter, and the value of the masses are all determined by the shape of these hidden dimensions in here. Trouble is in that right after that they found out there was more than one way that this thing could be folded up to hide the extra dimensions, and in fact it turned out to be almost infinite number of ways, 10 to the 500 possibilities for doing that, which of course really led to the unpredictability of string theory. But then this is the showstopper, the discovery in 1998 of what people are now calling dark energy, because they measured using supernova standard candles. They were able to measure the rate of expansion of the universe. We know it's all expanding, right? And they're saying, well, no, look, this rate is changing. It was not expanding as fast in the years gone by as it is now. And so that meant in the equations of Einstein, see, he had something called the cosmological zero to keep the universe, his equations describing the universe, to keep it from expanding, because at the time his equations came out, they thought it was a static universe. And his equations showed that it should be expanding. And so he had to set that cosmological zero, cosmological constant to zero, and called it his biggest blunder in order to make it a static universe. And then when they found out from the Hubble, Edwin Hubble's discovery that the universe was actually expanding, but it wasn't static, then he says, oh, that was my greatest blunder in my life. And he could have been predicting that they would have found that the universe was expanding if he hadn't taken the other route and tried to put his constant back down to zero. Well, now, when they made this measurement in 1998, they were trying to find out how the universe, if it's going to expand, what's going to happen? What would you think would happen? It would stop, right, at some point, and then start the big crunch, right? So they went out to try to measure, well, how much has this slowed down? And of course, to their astonishment, they found it wasn't slowing down, it was actually increasing. The rate of expansion was increasing. So that's why these occurred, right? Because that's a non-linear rate of expansion there. Well, the thing is, in the equations, what causes this expansion are the properties of the vacuum. And you see the vacuum, and Eisenberg's uncertainty principle leads to the theoretical conclusion that the force between two particles, which depends upon the distance between them, is due to the dynamics of the fluctuating field in the quantum vacuum. Well, this presents a huge problem. We're going to see what the fluctuating vacuum is here.
A picture of a quantum vacuum as calculated using our theory of the strong nuclear force, quantum chromodynamics, which gives the dominant contributions to what's going on in the vacuum at length scales of a nucleus, which is 10 to the minus 13 centimeters. This is what the vacuum looks like. Those fluctuating stuff are the quantum
fields. I cut it off too soon. Are the quantum fields. See? So this was a big problem with that kind of a boiling thing going on in the vacuum, supposedly. Then this tremendous energy, this energy has to be zeroed out, this 0 point energy, but if it's not zero, then let me back up. Their calculations didn't show that it was zero. The calculations of quantum field theory and even of string theory, but of all the theories, we could not calculate a zero energy in the vacuum. It had to be something that canceled, a cancellation mechanism that canceled it and made it look like zero, but it couldn't be zero. But they were always hoping that they'd find this cancellation mechanism. that would make their calculations collapse to zero because their calculations were just huge. And string theory, when they discovered supersymmetry, did that. And oh man, they were all excited until it dawned on them that the supersymmetry has to be broken at low energy levels. And when they realized that, then broken supersymmetry leads to this. It's not infinite. This is infinite up here without the strings, but with string theory, it's still big enough. It might as well be infinite because the energy is so great that Einstein's equations would have every little proton being its own little cell scattered, like it was. They would never come together. So, what is one to think? Well, the professionals are divided. It's really a crisis. Lee Smolin wrote the book and he called it The Trouble with Physics, String Theory and the End of Science. And the reason he called it End of Science is this anthropic principle that many of them have adopted that, hey, the universe is what it is because we're here. There's no way to predict the fact that we would live in a universe like this because there's a gazillion multiverses. There's a gazillion universes in the multiverse. And we just happen, like bugs that happen to come across an area of nutrients in a almost empty petri dish. We just happen to find a spot where we can grow and flourish. And so now we observe the universe the way it is. Well, that's crazy. People don't want to believe that. This guy here, Peter Boyd, wrote Not Even Wrong, a book at the same time that Lee Smolin wrote. And he's just saying that these people are just crazy. That he argues that the landscape of the non-unique solutions and lack of predictive power because it implies a non-scientific theory. That is, string theory. The string theory landscape is just untestable, and he calls it pseudoscience. And there's a big controversy. David Gross calls these two books Not Even Wrong and The Trouble with Physics. He calls them silly books because he's part of this group that are still working on it and believe that it's coming, that it will eventually work out. He argues that the achievements of string theory, says, while purely academic at this point, are nevertheless substantial, implying that a breakthrough is looming and that the revolution is coming. All right? And then he talks about how they attack the small cosmological constant problem, and I won't go into that, we don't need to, but essentially they take this and work backwards logarithmically to show how you get to the size of the proton as the energy gets lower and lower, because then the protons finally reach a point where they can't escape, the quarks finally reach a point where they can't escape one another, and as a result, that defines the size of the proton, all right? And so he's trying to show here, and that's within an order of magnitude, that they can calculate this. But what he's saying is, well, calculations don't mean much if you don't have a physical principle to go along with it. This is the great unknown. Just like Ed Whitten said, we don't know where all this stuff is coming from. It's great that it works out, but why in the heck is it working out? We don't understand why it does it. And this is the great unknown. He says the string theory can be constructed in many ways, even without strings. And I really don't know what he means by that, but these constructions, these different constructions, have no meaning. Something is still missing after 40 years. He says they thought for a while that it might not be a theory. Maybe it's just a framework like quantum field theory, but then it can't be a framework because it doesn't have these free parameters. So, it just is what it is. So it can't be a framework. So what they conclude then is that the principle, whatever the missing principle is highly fundamental. It's something very fundamental about reality that we don't understand. And it must have, the other thing that they realize is it must have universal scope. Whatever it is, it affects everything, right? And so then they come to, well, what's the most fundamental? The most fundamental is space and time, right? And what they're discovering with string theory research is that the nature of space and time is really paradoxical when you get to string theory. And Wynne said this: space and time may be doomed. and he wasn't the first one to say this. Way back in Einstein's day, Minkowski said the same thing, really. And then this guy, Seaberg, says, I'm almost certain that space and time are illusions. Well, what's the impact of that? Well, if we ask ourselves, what is the nature of space? And the answer is, it's emergent. And they've got lots of examples in string theory that says some or all of space is not really fundamental and only emerges at large distances in classical approximations. And what does that tell us? Because see, what they've done, you know, if you understand general relativity, what they did is combine, well, how many dimensions in general relativity? No, that's in string theory. But in general relativity, Einstein's general relativity, there's 4, right? 3 space dimensions and time dimension, and they're joined together, so time becomes like another space dimension alone. And so if it's emergent, if space-time is emergent, what does that say about time? Space is emergent and time, if they're hooked together, really. So this is what he's saying, implications of emergent space. If initially there's no space, then initially there's no space-time gravity. That dynamics of space could never work out. And if space-time is emergent, then time must be also emergent. But how do we do physics without time? And he's right. You know, there's no possibility that you can imagine that you can do physics without time. And so he says, this is the great perplexing obstacle, the conceptual block to our progress with string theory. It's amazing. All right, so how do we do physics without time? We have no idea. So the conclusion is then that the coming revolution will constitute a major change in our understanding of the nature of space and time. And then, and I tried to get the audio part so you could hear David Gross actually say this as well as read it, but this is what he said. It probably requires a young Heisenberg sitting somewhere to fiddle with something totally off in left field that will lead to these new concepts. And you guys are the young Heisenberg, see? So that's why I wanted a bunch of young people here to look at this. All right, now here's Heisenberg. We're going to listen to him here talk about this.
At that time, there was a general discussion among the young physicists about the possible ways to establish a coherent quantum theory, coherent quantum mechanics, and among the many attempts, the most interesting for me was the attempt of Kramers to study the dispersion of atoms, and so I tried to apply a mathematical calculus, which later turned out to be matrix mechanics, to the experiments of Kramers and to more general mechanical models of the atom. It just so happened that I became a little bit ill, so I had to spend a holiday on an island. So it was there that I really came to this scheme of quantum mechanics and tried to develop it in a closed mathematical form.
So he did, and it was on this island. And when what he was doing, he didn't know it was matrix theory, like he said, but he was putting a table together, a matrix, right, of the actual observables. That's the point. He was using. He was using the idea that things ought to be observable. See, Bohr had this idea that the electron, as a wave, could only fit so many cycles around the nucleus. And when it went up to another energy, the reason it was a discrete energy was because you had to fit one more cycle or a certain number of cycles in there. You couldn't put part of a cycle in there, right? And they were trying to make this work out, and they couldn't make it work out. And Heisenberg said, no, we got to go to observables. So he started making tables of what they were actually observing. And when he put them all together and studied, he was on this island, he was sick, he had a hay fever so bad that when the landlady saw him when he came here for vacation, he took the boat, this is off the coast of Germany in the North Sea, and he got to her house, and she thought he'd been beat up like a professional boxer. He was all puffed up and everything from the hay fever. But in the solitude, there's hardly anybody on this island. You can see there's no trees or anything. That's just that might be a little bit of grass, but there's not much. And then there's this big old rock that just sticks up like a tower right here. And so he working in that place, and he wanted to go climb this tower that we saw, and but he was working on it, putting those tables together, and lo and behold, he realized that he could conserve energy if he had this weird multiplication. It's called non-commutative multiplication, right? So that, you know, I know you guys have seen this, right, in algebra. What's A times B minus B times A? Huh?
0.
Somebody say it louder.
0.
0, right? 5 times 6 minus 6 times 5 is going to be 0. Well, he found that it wasn't. That if you switched the order and took the difference, there was always a minimum amount, a minimum number that it was, and that turns out to be IH, or H over I, Planck's constant over I. So he was astounded. And when he discovered this, but he didn't know. He didn't even want to mention it, because how's he going to explain this weird multiplication?
At that time, there was a general
And so he says that it had become clear to me what precisely had to take place of the Bohr-Sommerfeld quantum conditions. I was when he discovered this, he says, I was far too excited to sleep. And so as the new day dawned, I made for the southern tip of the island where I had been longing to climb a rock jutting out into the sea. I now did so without too much trouble, and I waited for the sun to rise. So if this is the rock, I don't know if it really is. That's quite a rock to climb, right? And he gets up there at the top, and he's waiting for sunrise to come up, just thinking about what he discovered, meaning it was bringing in a new age. He knew it was. See? And it certainly did, because that was the dawn of quantum mechanics. That's where it all started, when he discovered that weird multiplication. So I thought that was really interesting.